How's it going, everyone? Euler Gonzalez here, exploring now the point-free techniques and closure in today's video, and that'll be quite interesting since we're gonna make a quick recap of how do we get here. So by exploring all of these different techniques, and pretty much like when you go out into a restaurant, you don't need all of the mathematical fundamentals of the arithmetics, so the addition, subtraction, division, multiplications, not to mention that where is the reason of why numbers kicks in? What is the mathematical proof of that? It is interesting, but it's quite not practical or might be irrelevant for your daily life, right? Now, that's the value proposition of this functional programming taught by Kyle Simpson. That is, we're gonna give you, and we're gonna look and explore and see how you can use this kind of tools for functional programming that they sit on this ivory tower, all right? And we're gonna see that at the end of the day, it's not that hard to understand. You just need to look at how they see things. It's like using a special sunglasses. When you wear them, you now can see is you have now these special powers. All right. So this is their vision, their mindset that we want to now look at them as a way to say, hey, anytime you're going to write user interface or you're going to use JavaScript and so on and so forth, it is good to have this kind of techniques at hand so we can first identify what it is, which is something that we're going to describe briefly here. Second, then know when to apply it, because this is where decision making, judgment kicks in. So the value proposition, as I mentioned before, is that by relying on this mathematical proof, we don't need to try to rediscover, reinventing the wheel, or prove those fundamentals. So we lay out, or we can rest assured on the mathematical bedrock that those kind of stuff, those kind of stuff will gonna work as long as you use them in that regard. So we have now, or we have looked so far, is what is a function, what is a procedure, what is the difference between them, and also the type signature, which is the shape of the functions, and how now functional programmers are obsessed with the shape, because this is pretty much like when you have Lego blocks, where you try to fit one into another, that the shape or how you can now is fit one function with another is crucial, because as long as you can now is find ways to adapt those shapes, you can make all of these different functions works together. And some techniques that by the time that you write a function that has the same shapes, it is much more clear to see the relationship between them. So the point-free techniques, that's the value proposition of this. So instead of having, or instead of declarative, having to pass is the number of arguments, or define the data points, aka that is inputs. So as long as they have the same shape, what we're buying with this technique is, this will help us here is with the readability of the code. So we can see is the relationship between the code much more easy. So yeah, that's actually what we went through all of this. In today's video, we're going to explore these 2 points. First is this introduction about what this functional programming is. That is lay out the mathematical proof, as I mentioned before, where the idea is that you don't need to think or to mathematically prove all of those tools that you're going to put in your tool belt. You just only know when to use it, what it is, and by the time and when you need it, you just apply it. So because this is a different mindset of how you can look at things, so pretty much like 420, okay? That if you're not quite familiar with 420, once you know, it's like, oh, it's like a different mindset. Pretty much when you hit the gym and then you're starting to lift some heavy weight, it is a different mindset. And for those who knows combat, let's say some MMA, it is also a different mindset of how you're gonna do a particular task, whether it's boxing or kickboxing, judo, all of those. But my point here is that it is a mindset, it is a vision, it is a special sunglasses that at the end of the day, anytime when you look at this kind of stuff, you know what to do and when it comes and what is the outcomes that you're going to get from. So this is a journey that have a quite learning curve, because initially you're going to come from imperative programming and then you're going to move forward to a more declarative. This is the approach of this course, which is something that I really love about this. Unlike talking about all of these high level concepts, I'm going to see how we can now use with what we have, what we know, and then progressively do shifting to that mindset, to that way of doing things. So to do that, we need to look at what is a function and a procedure. We went through that by looking at the inputs and the outputs and the relationship between this input and this computed output is what makes a function. And to take advantage of this useful stuff, or to take advantage of the benefit of using now functions, we need to set a set of rules, set of boundaries that will make us sure, that will give us confidence that anytime that we have to use these functions, anytime that we need to call this function specifically, we know that that function won't run into some side effects. And side effects in computer science is anything that changes the state of this function outside of this, or at some point that you, for example, need to, if you are a JavaScript developer, well, you need to wait for it on to load, or reading a database, or a network call, or generating random numbers, or timestamp, or anything that ultimately generates CPU hits or CPU time delayed. So for those cases, which eventually at some point it needs to happen, well, we need to reduce the side effect. So we first look at these side effects. How can we create functions that don't have side effects? And that is by following a particular techniques, which is something that is here, for example, like this, all right, where you can know how you can create or how you can write your pure function and then your impure functions. And the idea of this is that to create this pure function or this function without side effects first, it is important to understand that the less reassignment that happens inside of a function, the better off will be for you, because you have now much more confidence that that will work as expected. So that's why we look at this kind of techniques when you have now a function that returns another function, and so on and so forth. All right. So by reducing the surface area, especially when you're defining your function, this is the way of how you can create your pure functions in terms of definition. But most of the time we need to is use somebody else's functions, right? Let's say you need to is use a function that read to a database or do a network call, all right? And for those cases, how can we now is extract the impurity of that? And there are two techniques that at least now Kyle Simpson show up. One is that by looking is at the function purity calls, not definitions, and by extracting their impurity here is by taking the lexical scope right, or containing the lexical scope. This is at definition, all right, and the other is the function definition, and the other is at function runtime, which is containing impurity in that case. When you need to write your function for functions definitions, containing the lexical scope is a good technique of how you can actually extract the impurity of that. However, when you need to call a function for function at runtime, you can wrap is a function from that. And now this is part of the brute force technique, at least in 2017. You put all of those, or you take a snapshot of everything that it needs to, and then you restore the state afterwards. Because unlike functions definitions that you cannot contain is the scope of that, on function execution, where the value of this is now when that was called, you want is to make sure that whatever state that function are modifying, you want to take a snapshot of everything, runs that function, all right, and then restore the state that it modified afterwards. And that's exactly what we are looking at. And that technique is something that lay out the fundamental of this vision of putting this on glasses of when you need to is define your functions in a pure way, as well as how you can is extract the impurity, which is most of the time what you gotta do. Again, sometimes that technique is quite expensive to do, especially the brute force, which is the function execution. But at least you have some technique of how you can do that. Now, then we look at the adapter arguments, the difference between the parameter and the adapters. So parameters are the names of the inputs from the point of view of the function's definition, and the argument is the value that we pass in. So why this is important? Because functional programmers are quite obsessed, as I mentioned before, of the shape of the function, and it's interest is is important, and it will lay out the foundation of what's coming next. All right, understand the shape of a function, understand that is or this type signature, and to be more easy to grasp on is the number and the shape of stuff that you pass into a function, and the number and stuff that come out of it. All right, that's the function shape. So the most favorite functions or shape of the functions that functional programmers love are unity functions, and the second one is binary functions. Okay, so here we're talking about in terms of its arguments, and this is important because even though that arguments and parameters are technical, are used interchangeable, they are technically different. So the idea here is that by exploring of how this functional programming library works, especially of how now they take the arguments and then reshape that, okay, whether it's a unity or a binary, and then apply some sort of transformations to this shape, all right. With flip, for example, let's going to now is change the order of the arguments. So we create now some higher order functions, which is just a fancy way to say, hey, this functions receive is a function or a set of instructions, or this functions return is a function, a set of instructions. So we do this kind of higher order functions is just to actually is transform into something. All right. So in our case, we define is now the unity, where we take now the function, all right, and we're gonna only get is the first parameter in this case, or the binary function, and the second argument is you're gonna take is only the two arguments of that. So we also look at the flip. All right, we're going to take all of the arguments from this and flip the first two parameters, okay, and some other stuff that you can do and you can use it. Why we're looking at this? Because if you're going to use in a functional programming library, you want to get used to that, whether it's Lodash or Randa, and since this is now part of the community, so we are familiar with this set of tools, so anytime that you need to come up with some sort of new particularly techniques or tools that you see use is that you constantly using that, or that you see yourself using that here and there, now it is time to, well, make a PR and then now make that tool available for somebody else, for others, or even for you from the future. So you can now get yourself familiar with all of these tools, and when you see something weird, or let's say you're reading some code and you say, what is this? It's like, you know, now you're, the idea here is to get yourself familiar with this tool and also make others aware of these tools and when to use it. Something that we're gonna see that at the end of this course. But in any case, we also talk about this particularly techniques called point free. That is pretty much like when you go out to, or if you went through 8th grade, all right, and your math teacher tells you to fix a point on a Cartesian, on the Cartesian graph. Let's say you're gonna fix is the point of G, right? Say in 2. So if you do that, any x value will draw is a line to that, right? So why this is important? Because with point free, or in other words, data points, we are now being able to look at these data points, aka these inputs, functions inputs, that when we fix is the value or the argument of an input, all right, we can now is use that as a way to now make those or use those functional or use those functions with this presets value, all right, which is something that we a lot of the time we see in this presets value, all right, when you have these functions that have this particularly predefined values. And the idea of this is with the point free technique is that what we are buying here is that increase the relationship between the different functions that you are calling here. So make it clear the relationship when you're writing your code. And despite that, this technique doesn't show you is the arguments, all right? Because it says, hey, if the arguments of this function is the same, or is the shape of this function is the same shape as this another function, right? Let's going to define that in terms of this equational reasoning, in terms of its equal shape. So this is when the readability of your code tanks, because now you have all of this identifier that look like a variable, but at the end of the day they are just function without its data point, because now the idea here, what we're buying here, is to see clearly the relationship. So if you ask myself, any functional programmer or any programmer, that what is better, is being descriptive or implicit, most of the time we're gonna say, hey, it's better to be explicit. That, but here we are exchanging the explicitity you get it. But here we are exchanging is being implicit or being explicit with this implicity, so for an outcome. Now this technique, all right, is to me quite interesting. For example, like this, right? So by defining now here is this particularly high order function. And again, I don't expect you to grasp this on one go, because this is something that might require you to take quite a bit of time and practice and exercise, so you can develop an instance, a second nature of that. Right now I'm taking boxing and MMA class, so what I'm looking at here is that this particular mindset that I'm getting here is especially, or this particular movie, when you take this, this particular movie that we're passing in front of our eyes, that anytime that pass here, we just need to react, bro. And that's exactly here when we're looking at this. What we are getting from here is that, oh, it makes sense that anytime that we look for these particular techniques or tools, we know what we're getting from. And then you just automatically evaluate that. So look at that movie pretty fast. And then ultimately, well, get the outcomes. The outcome here is that make our code provable, easy to read, to understand, and to debug. And now from MMA, which is of course I only have is 6th class, but from MMA is to have now all of these different techniques here in a way that when you need to do that, you don't think about it. You know the moment, you know the situation, so you can act accordingly. And that doesn't mean to fight, but that's what I say, act accordingly. So in any case, here we are, right? So we create this not function, which is now it's going to take that function and its arguments, and it's going to negate that. All right. So by the time that we do this, and instead of having to say, so instead of putting the relationship in its mathematical proof like this, all right, we can rewrite this in terms of it is complement, or it is negate, right? In terms of it is semantics. So function is odd, and this is how we can now say, hey, I would like to write this in as the opposite, as the complement, as the negate. I prefer to call that negate. Complementary is something that is quite confusing. Again, it's a mathematical term, but I find out that negate is something that is much more straightforward. So not only for this, because we also look at exercise on GitHub here. Exercise here, right? Exactly, exercise here, like the point-free challenge, right? So this point-free challenge, because at the end of the day, we want us to know is how can we transform is some functions definitions into, some functions definitions into point-free style, which is not an easy stuff, right? So we can now see the relationship much more clear. So for example, for console log, we did that pretty straightforward. For it is negated as well. And when you need to actually is, for example, that this one, which was more not that easy to look, the print if, all right? Because if we want to transform now this function into a point-free style, so this print if that is receiving is what is going to print, all right? Should print it, all right? Is like the predicate, okay? Should print it. We're going to receive is now the argument, all right? And print if like this. So that's actually, let's going to now rewrite this, right? It's going to do this one. It's going to do is this. That's a lot. There you got it. So instead of doing this like so, all right, if we want to transform all of this into, you know what, let's gonna use here is this one. So here we can rewrite this console log in like this. You say, hey, output, which now will be is a output, which will be an identifier where we want to host is a function console log. Here we are not calling it. We want us to now have access to the console log to say bind the value of this, just like that. So what we're doing is anytime that you now use the output, I want you to now is use the console log. Okay. So in other words, for example, it would say something like this. Output console log here. Okay, so what I'm saying is that anytime that I want to use output, I want to now is use the console log function, all right, where as long as you pass this one single output, I'm gonna run that function. So in other words, you say something like this. Say output is the message one, right? And there you got it. So what we're doing is just reassigning that. We're using is bind because we want to tell this function that by the time that you run this function, this is the context. So far so good with this. Similar for the another function, which is, I think it is short enough. Yep, is long enough. Refactor output printf and is long enough. So is long enough is this one, right? So this is long enough. Clear. So it's long enough. So we want us to now is refactor this is long enough, because here we want us to say that in terms of its relationship by the function call. All right. Here we say, hey, function is long enough. Okay. Is long enough. All right, and this function is long enough. What we're gonna receive is now a string. Okay, we want to say, hey, I want you to now wrap this into a higher order function that will be called not. What I'm going to receive is that function. All right, and then I want to return this function. Call is long enough. All right, what we're gonna do is this. I want to now is what you're gonna call here is with the parameters, because this is the name. We're gonna call this functions predicate. Okay, because first we wanted to receive is the function and then the arguments. Okay. And we want to do is this. Return is now the negation of that function with the string, right? Here we are only taking one argument here. So in this way, so by the time that we say, hey, to rewrite now is long enough, instead of in terms of its function, we say now in terms of it is point free style to match that output. So is long enough. All right, it is a function that is going to call not, right, initially, and we're going to pass this now is sure enough. Okay, so here we have now the relationship much more clear, right? Way much more clear than it is. I'm not sure where we are using is long enough. Long enough. Exactly. And as you can see, it is this one. So it's long enough. It's actually showing is this. So, but the point here is that we are now seeing the relationship. We have now a more clear vision of what's going on. And this is just for simple examples, right? Because when we need to now rewrite this function here, the printf, which we want us to now describe in terms of it is point free style. Remember that the value proposition of point free is to make the code is provable, and that we can see clearly the relationship. That we can clearly see the relationship among them. All right. So now in terms of do a refactor of printf, all right, because this printf function say, hey, should print it and the message, all right, So now this is something that is provided by the example. We say, hey, when we define now a function here called when, a high order function, and when we take that function, all right, when we take that function and we now printf, okay, but in this case we're gonna call this predicate, okay, this function here with the predicate, all right, with function predicate that will tell us is that, hey, if this is the condition, the predicate we want to check, and we're gonna get now is the function data, which is the message here. So by the time that we call here, we're going to say, hey, if the function with the predicate is true, okay, if the function with the predicate is true, then I want you to now return is the function with the message. All right, so we can rewrite now printf in terms of its point-free style. Okay, in terms of its point-free style, output and when. Yeah, so output and when. And here, if you want to redefine this in terms of it is point-free style, we can say is print if, okay, it'll be now a function called when, and this function here is when this function, in our case, the function that we want to pass in here, the function that we want to evaluate here, which is when output, okay. So printf when output, and then you're going to now call that. So by the time that you're going to pass now the predicate and the message, it actually work as expected. It's a, hey, short enough, long enough. Oh, because here, yeah, it's returning a function here. It function predicate exactly, and return a function message here. In other words, call. Oh, I think it's because I don't need to call that. I just need to is run that, execute that. So don't return me anything here. Yeah, don't return me anything here. You say, hey, so don't return anything here. This one is to print that for that. Okay. In terms of its argument, because here we're taking is just one argument. Mm-hmm. Okay. No. It's because if the predicate is the same as the argument, now you're gonna call is the function. You're gonna return is the function here. Why is this important? Because we are actually wants to test that, to test this predicate. We want to test this predicate. Oh. I get it. And pass all of the arguments to that. And pass all of the arguments to that. And then you got it. I was going to keep exploring other advanced point techniques here.
There are certainly more advanced techniques. And I want to give you just a couple. This is just a quick glimpse at a couple of these, and we're going to come back to them later in both lecture and exercise. Okay? So if I defined a couple of utilities, and by the way, I'm not inventing these are ones that you would find in a functional programming library, but let's define one called mod. It's going to do modulus operation. It's doing something which might seem a little bit strange to you. I'm taking the first input mod on line 1, I'm taking y. And then I'm returning a new function called 4x. In other words, that function's purpose is to receive the x input. That's why I called it 4x. Okay? And when that has been provided, when we have provided a y first and then an x, those are two separate function calls where we provide two inputs one at a time, then what happens is it does x mod y. So we're providing them in a reverse order. That's going to feel a little strange to you, but I'll show you in just a moment why we're going to do that. And then I'm going to do the same thing with an EQ operator. An EQ utility, which takes a y and it takes an x, and then it returns us the equality comparison of those two. These two kinds of utilities, which take their inputs individually, rather than passing x, y at the same time, taking them in two separate function calls. We already saw a brief example of that in the question that was asked earlier. Is this sort of currying? Yes, this is basically a manual form of currying. We'll get to that. But I'm saying I want the y input first and then the x. And I want to make a point about that before we move on. Remember that I said earlier, functional programmers care a lot about the shape of their functions. It matters not just what kinds of inputs a function receives, but what order they're listed in. Because if you...
Functional programmers cares a lot of function shape. Because it's not only the arguments that receive.
You list the shape of their functions. It matters not just what kinds of inputs a function receives.
So it matters not only what kinds of inputs a function receives, but the order.
But what order they're listed in.
But what order are listed in.
Because if you list them in a different order, guess what people are going to have to do to use your function every time? Flip it, or use reverse args or something. You make it less ergonomically friendly.
Because if you if you change the order of the function, if you change the order of the function input, guess what people will use. Yeah, so guess what people will use. Yeah, guess what people will use. Will do shifting or flipping the order. So yeah, that's why we use this now a JSON.
Used when the inputs are listed in an unnatural order. So it matters what order. And what you're going to see here is actually there's an order that is much more natural, which is yx instead of xy. And yx instead of xy for the equals function. So that's why I've listed them in that particular order. Okay, so let's take a look at how. We could use this mod and this EQ function to define. Remember, we defined is even in terms of is odd. But what if we wanted to define is odd in a point variable? Remember, is odd was defined as x mod 2 equals 1. If we have these two utilities in play, couldn't we define is odd in terms of those two functions? So I'm going to take mod 2, mod parenthesis 2. That's going to return me back a function, right? Where the y has been provided, but the x still needs to be provided. And I'm going to call that function mod 2, because that function takes any input and mods it with the number 2. And then I'm going to call eq parenthesis 1 line 13, and that makes an eq1 function, whose job is to take any input value and compare it to the value 1, is equal to 1. Quick little foreshadowing to stuff we're going to talk about earlier. Do you see that the mod 2 function on line 12 is more specific than the general mod function on line 1? The general mod function on line 1 takes 2 inputs. The mod 2 function on line 12 only takes 1 input, because it's got one of them already pre-specified. That's a more specialized function. I'll come back to the idea of specialization. Okay? But I've got a mod 2 and an EQ1. How could I define is odd in terms of those functions? Well, it's actually pretty straightforward. Take the mod 2 and pass in the x, and whatever that returns, pass it into EQ1. Follow how I did that? Now that's not point free yet, but we've made a lot of progress moving from operators to functions.
Yeah.
Okay? So we're halfway there. If we want a point-free definition of is odd, this is halfway there. We notice that we have this EQ1 and this mod 2. They're useful to us, and we can make those with the mod and EQ operators that are provided by our favorite library. But we can also notice something interesting, and this is yet another future thing that we'll talk about later in this course, which is the output of the mod 2 call is passed directly to the EQ1 call. Everybody see that?
This is composition.
That concept of having one function calls output immediately becomes
the input of another
That
function.
is a special name in programming. That's called composition. Again, throw back to a math class. You may have heard somewhere like f sub g or f compose g. That's all a mathematical idea, and here we see it up in programming. Take one function's output and make it the input to another function. So how can I use the idea that this is a composition pattern to my advantage to make a point-free definition? Well, if I had a compose utility, here's my is odd. If I had a compose utility whose job was to do the routing of one function's output into another function's input, now line 14, I just define is odd as the composition of the EQ1 and the mod 2 function. Line 14 is my point-free definition for is odd. It's doing under the covers. Mod 2 is fn1, which is called with whatever value passed into it. That's line 10. So mod 2 here is this function. If we pass in a value into is odd, it would come into mod 2. Whatever that output is would come into fn2, which is EQ1. And EQ1 is going to return us a true false, just like we want is odd to. Okay? How am I able to make that analysis? This is more equational reasoning. That the function composed here is the same shape as is-odd, isn't it? Look at those two. Look at composed with an fn1 and an fn2, and look at is-odd with an fn1 and an fn2. Look at the input x, look at the input b, look at the return value and the return value. Those two are interchangeable, which is what lets me know that line 14 is my point-free definition. I simply call compose, and I get back to the equivalent function. That's the equational reasoning. And we have one last equational reasoning trick up our sleeve, which is on line 1 and line 2, I defined those intermediary functions, mod 2 and eq1. But now I can see that eq1 could be replaced with eq parentheses 1. And mod 2 could be replaced with mod parentheses 2. So my final point-free definition looks like line 16. Those pieces are interchangeable because they have the same shape. That's equation. And equational reasoning is the heart of being able to do point-free style. It's actually the heart of a bunch of functional programming, but especially point-free style. Asking yourself, if I have this function and I need to make this function, what kind of shape change needs to occur so that they're interchangeable? I'm pretty sure that at some point along the way, we crossed that line for all of you. We're like, oh, I never would have come up with that. At least that's how I was. When I first saw this, I was like, whoa, we just went way beyond what I thought was like, oh, I'm tracking with the readability and now I'm lost. And now I will just tell you that having spent time practicing this, and I'm fortunate enough that as a teacher I get to re-explain it and re-show it and recode it over and over and over again, and that's my practice. But in being able to practice this, I will tell you, not only can I read line 16 and understand it, line 16 is more readable to me than line 5. I've gotten to the point where that familiarity level has switched to where the point-free functional style is actually more readable. And whenever I see something like line 5, immediately my brain says, that's a composition, you should be using compose then. I didn't get there overnight. It didn't happen in a week. It didn't happen in a month. But over a period of time of practicing these techniques, you become more familiar with those patterns, and they start to jump out at you just like you see the Legos in the pile and you say, nope, I know exactly what it is. That's the heart of being a functional programmer. It's getting used to that, being able to recognize that, and then being able to read stuff like line 16 and have it make complete sense. All right, so we've already hinted at the idea of closure in this course. A couple of times we've already used it. But I want to be very specific about a definition for closure, because there's a lot of misconception about this concept, and it is absolutely essential.
Is this what? Okay, so with point free, okay, with point free, that since a lot of the time functional programmers cares a lot of the shape of the function, and not only is of what kind of input that we put in, that we pass it, that this function receive, but what order are listening. And because if you change the order of the function inputs, guess what people would do? Well, flipping the order. Now, the idea here is that by exploring at this way, so by exploring utility functions, because it all starts with this is the story here. So by exploring utility functions, so by exploring utility functions such as mod and equal, okay, that they are based on mathematical proof. All right, like this one is like, hey, we're gonna use as a model of this, or the model, or the equality here in equal values, okay, that they are based on mathematical proof. So by exploring utility functions such as mod and EQ, that they are based on mathematical proof, and describe them in a point-free style, so we can use, so we can reuse them, or aka compose them, to see their relationship much more clearly. And that is by looking at that now at this function. But definitely we make sense of the word through stories, bro. Definitely we make sense of the word through stories, bro. Oh yeah, it is. Make no mistake. Make no mistake about it. Which is this. So now with the compose function, we can now call functions that allowing us to see the relationship between them, between function calls. So we can express statements in a more meaningful or in a more semantic way to the reader. For example, here you say, hey, var is odd, compose equal 1 and mod 2. So I'm going to compose this to function, which means that I'm going to call is the most right function first. Mod is the mod 2. What is the model of 2? Which is 2. And if that is equal to 1, and if that it is, then it is odd.
All right, so we've already hinted at the idea of closure in this course. A couple of times we've already used it. But I want to be very specific about a definition for closure, because there's a lot of misconception about this concept, and it is absolutely essential. You just cannot do functional programming without a solid understanding of closure. So I want to give you a very specific
closure. In singular.
specific definition for closure that is based upon what we can observe in our program. And that is, closure is when a function remembers the variables around it, even when that function is executed on it. And by around it, I mean any variables that you access outside of the function. They aren't directly passed in. They're accessed, like, remember when we access global variables, things like that. Anytime you access a variable from an outer scope, and then you take that function that is doing that access and you pass it somewhere else, and you run it in a different scope. If you thought about it logically, you'd say, well, it should forget about that variable because it's running in a different scope. But it doesn't forget about the variable. And the reason it doesn't is because of closure. And if that sounds too abstract to you, let me remind you that we've already seen this several times in code we've looked at. Here's an example. I'm illustrating the idea of closure here. I have a make counter function. Make counter doesn't take any inputs in. It declares a variable line 2 called counter. And it returns us back a function, which every time we call it, is going to increment that counter variable. So on line 8, I make my counter. I say var c equals make counter. And I call c with no inputs and I get back to value 1. And then I call C with no inputs and I get back to value 2, and then 3, and then 4. So it's in a counter, right? Could be useful in our programs to have a counter. Well, let me ask you, this is definitely closure because we have the inner function increment closing over that counter variable. It's remembering it. Even though make counter has finished, the C function still remembers it and can still keep updating it. That's how it works. That's called closure. But I want to ask you, is the C function a pure function call?
Yeah.
Look at line 10, 11, and 12. Are those pure function calls?
Yeah.
It's not pulling from the DOM. We are not getting the same output every time. We're passing in the same input.
Oh, exactly. So you're not getting the same output. Exactly.
No input. But every time we're getting a different output. So it absolutely violates one of the fundamental premises of a pure function. So here's the takeaway. Closure is not necessarily functionally pure. But closure can absolutely be used in functional pure. So the key is, if I'm closing over a variable, this counter, it can't be reassigned. If it's getting reassigned every time, that's a big no-no, because now we are not closed over a constant anymore. We're just closed over some changing state, in which case we now have an impure function. You might have to do that in your program, but that's not going to be a pure function. You with me? So let's look at some examples of using closure that is consistent with functional style, that is going to produce a pure function. Remember unary? That was one of the first utilities that we looked at, our first higher order function. It takes in an fn, and it remembers that fn, and it uses it later. How does it do that? Why did the fn variable from line 1, the parameter, not get garbage collected when unary finished? The answer is because the inner function 1, which got returned, is holding on to that parameter via what we call closure. It still has access to that. So later on, whenever we call f somewhere, it still remembers the original thing that was passed in by way of the parameter fn. And that's not the only example we saw of closure. Remember add another? We talked about this one. Remember how it's referencing that z variable, even though that z variable was passed in an outer scope? The add2 function is closed over the variable z, which is why it's able to use that later on.
The add2 function is closed over. This way of describing here.
Referencing that z variable, even though that z variable was passed in an outer scope.
The add another function is
add2 function is closed over the variable z.
Is the add2 function is close over. But close over in Spanish. Close over file. Archivar. Close over. The function add2 close over the parameter c.
Why it's able to use that. The variable was passed in an outer scope. We saw a closure. Remember add another? We talked about this one. Remember how it's referencing that z variable, even though that z variable was passed in an outer scope? The add2 function is closed over the variable z, which is why it's able to use that later on. And the key thing here is that in both of those slides, the fn on the previous slide and the z on this slide, in both of those cases, we are referencing a variable outside of ourselves, which seems like it would be a no-no, but it's safe functionally because it doesn't change. It's a memory over a thing that doesn't get modified. That's what makes it still functional. Let's do a practice exercise on this topic of closure. It feels like a really important topic. We're probably going to keep coming against it over and over again in functional programming. It's good for us to get some more exposure to it. In this exercise, we're going to practice closure by building a utility. It may seem a little strange, but building up a utility that we'll call string builder. If you look at the exercise and specifically look at the test cases down at the bottom, you'll see what this is supposed to be able to do. We're supposed to be able to call this function, string builder, and pass it a single string. And then if we call it again with another string and another string and another string, we can just keep adding more and more strings to it until we call it once without any input. And then it's going to go back and concatenate all of those strings together to give us one final string. And also, not only will it do that, but we should be able to capture those individual specialized functions. So we should be able to capture, for example, hello is the intermediate function after string builder was called with hello. And we should be able to call this twice, producing two different functions, in this case Kyle and Susan. And then we should be able to call Kyle again, and when we call it with nothing, this question should come back as the actual string. Greeting should come back as the actual string. Okay? This is a bit of a challenging exercise. A little bit of a hint can be seen in the README, so you should definitely check out these hints. It should be able to give you everything that you need, but it will be a little bit tricky and challenging. Make sure all of the test cases pass. Let's talk about the solution to our exercise on closure. Now, I am just going to forewarn you, I am going to deliberately solve this incorrectly to prove a point about the way that we think about closure and what it means for functional programming. Then we're going to solve it correctly. So the first thing to note is that string builder, when called with a string, returns back what?
Must return a function.
Returns back another function that's expecting to be called with another string. So it's going to keep returning back a function, and it would do that essentially forever. As long as you keep passing strings, even empty strings, it's just going to keep returning back a function. So what does that pattern look like? Well, we know at a minimum, we've got to make and return a function. So I'm going to just call this function next because it's just sitting there waiting for the next string, next string, next string, okay? That function is going to receive...
It's looking for the next string, next string, next string. It's sitting there.
We're not sure if it's a string, it's going to receive a value. Now, I want to keep going, if you will. In other words, I want to return a function if the value that was passed in was a string. Keep going as long as it's a string. As soon as it becomes not a string, that's when I'm going to bail it, okay? But I need to keep track of the strings that I've seen so far, because I'm going to keep returning this thing back over and over and over again. I'm going to keep track of those strings in some way, and it seems natural that I might just start concatenating it onto the string. So if I receive value, and if I receive a value that is of type string, then what I know is that I could just concatenate it onto the end of str, right? Because that was my initial string, and then I can just start concatenating stuff onto the end of it as I see it until I don't see a string, and then just I need to return string. That's a convenient way of keeping track of it. So if I just said string plus equal to v, and then otherwise, in other words, so if it was a string and I concatenated it on, what do I want to do? I want to return that next function again. Just the function itself next. So that I just keep returning a function back until I pass in something that's not a string, and that's my signal to return whatever it is. Did you follow that thought process that I went through? I need somewhere to store all those values, and it seems logical that I just throw them onto the end of the string, and that'll be a good place to store. And how do I know if I need to keep going with a new function or not? It's whether I would pass in a string or not. Everybody with me? Now, if I take this code, this is deliberately the wrong solution, and I'll explain why in a moment, but if I take this code and we try to run it, we'll notice that I get several failed tests. But notice something interesting. The test that did succeed is the most seemingly complex of the tests. It's the one that was called a bunch of times. That one passed, and it's all these ones that didn't pass. And there's a clue there. If you pay close attention, there's a clue there as to why our solution didn't work. And the clue is that what we have are these intermediary functions. Notice I've got Kyle and Susan. Those are sort of a fork, if you will, from hello, where we're going to end up with hello Kyle and hello Susan. But if I have modified string with the word Kyle, and then I try to call Susan, if this function is closed over that same string and I've modified string, that string no longer says hello, now it says hello Kyle. And I'm trying to put Susan onto the end of hello Kyle. Follow me? So that's really kind of where our problem is stemming, is that if you think about it, what we're doing is we're closing over a variable that's being modified each time. So in other words, we have functional impurity. And that's why this is not working, because we have functional impurity. So I'm going to go back and try to solve this in a different way that preserves the functional purity. Okay? So let's start over. Well, I'll leave the function next part, but let's rewrite this part. So we know now that we never want string to be modified. We're closing over this thing, which is what this inner function will be doing. We want to only close over string that stays the same. Okay? So I do still want to do a test. I want to say if the type of V is string, then I want to do something, and I am going to return something here, so we'll do that. If I don't return a string, then what is it that I want to return? Now this is the part that's maybe going to be a little bit counterintuitive. Let's talk about what happens if the string, we need to figure out what we're putting here. Let's talk about what happens if we have passed in a V that is a string. We have str, whatever value it currently has, and we have V. We don't want to modify string, but what we want is a new function that will wait for the next string, and that new function needs to know about both string and V. So in other words, what I really want to do is I want to call string builder again. I want to actually call it, not return it. Now when I call string builder, what is it going to return? It's going to return
a function, another function.
But when I pass into string builder is it's the new partially concatenated string. I'm not modifying the variable that I'm closing from. I am calling to the next level. So when this is almost recursive, it's not exactly recursive. But when string builder comes back in, this string is now going to be the 2. We're closed over the 2 string. We do it again, now it's a bigger string. We're closing over a bigger and bigger string. But every single level of that closure is only ever closing over one value. So what if I didn't get a V? Well, now I just return. The V wasn't a string. It was underlined, it wasn't a string. And I know that whatever this was last time was the end value of the string. Test myself to make sure. So, key takeaway here is that if you're going to use closure in functional programming, you have to make sure as soon as you start mutating values that are closed over, you lose your functional purity, and it won't often be a catastrophic test failure like I said. It'll often be an extremely subtle bug that only comes up once every 4 requests. That'll be what you're facing. So one of the takeaways that I'm hoping that you're getting from this course is that if we code using these functional principles, we actually avoid entire classes of bugs that could have happened otherwise. They're just not even possible to happen because of the principles of functional programming being so sound and mathematical. So if we close over never changing values, we're far less likely to have one of those bizarre string
Well, that'll be all for this video.
On this topic of
Take care. Bye-bye.